Okay. Sorry, the stream got cut off there. Somehow it got dropped. Let me just check and make sure we're back up and running. My video's okay, my sound's okay. Cool. I'm not sure where brief reflection on what we... Oh, sorry about that. So we had covered mutability, which is kind of an important idea in Python, which is this concept that a variable is a pointer to some object, which is an object is a structure for representing data. The object may or may not have the capacity to change its value. So you end up pointing the variable. For instance, if you have x equals x plus 1 or something, then what you do is you actually point x to a different object. Whereas something like a list or a dictionary or a set, a list, for example, has a method called append. It has other methods that will change the value of the list. So like append, sort, reverse, pop, things like that. Those will cause the object is still the same object, and the variable still points at the same object. Change, and some objects they can't. The ones that can change are known as mutable. So the ones that can't change are known as integers, floating point numbers, Booleans, strings, tuples, things like that. So similar to variables in terms of the way you mod 7, and it takes in a parameter that we call in. But unlike a variable, we don't give it a value when we define it. So it's just a name, and it doesn't have a value in here, right? Because in here, the definition, we can just replace anywhere. So for any one of these calls, we can just replace wherever we see n with the number supplied in the input. So we return n times 3 mod 7. And for this first function call, we can just imagine this as return c mod 7, etc. So it behaves a lot like a variable. It's an identifier that's value. When we define it, we supply that object when we call it. Whereas as a variable, the name for the name part of the variable, right? So that's some identifier. I don't. Okay. So that's a parameter versus a variable. Then we also talked about variable scope. Oh no, is this... Give me a second, is this crashed? That's okay. Excuse me, my Chrome appears to have crashed. Let me just restart this. Looks like it's probably me though. You know, it's always operator error. Not really, but you know, it cool. Hopefully that's going to work. So variable scope. Okay. It being weird. This is a matter of understanding when and where certain variables and parameters, identifiers, are accessible, and how perhaps if you have something in the global scope and something in a local scope, that are named the same thing, which object is going to take precedence over the other, right? So let's say we have x equals 5, and we say def some function takes in x, print, and let's just say we're going to return x. Okay, so expect this code to do, right? Let's run it and find out. I see code that all the mistakes are good. You want to make them all the time. Okay, so this says type error, func is missing one required positional argument. So it's a positional argument because it has to come in a certain order. I don't have to name it, give it an explicit name. So you can see I'm returning x here. I'm stating explicitly that I want to take in a parameter called x. Here does not need to be called x. X is only a name that applies internally into this function, right? So let's create a variable called y and make it equal to 77 or something of y, and that's just going to return 77, right? So notice this x up here have on this function. Well, in this case, none. It doesn't matter at all, right? In almost all circumstances, you shouldn't. And I really mean it. Like I've never encountered a circumstance where I couldn't solve a problem without doing this. There are cases where writing code like this might be desirable, although like I said, I've never encountered it in reality. The only reason that I can think, and then there's just some process that would be optimized by doing this. Although I think if that were the case, it would be more of a stopgap measure. There's probably still a better way to do it. It's just like if you're working and that it exists, I could say return. Oh, fortunately, this gives me a name error, which is nice. Let's call this z. Okay, so this allows me access. If I want to pull in a global variable into my function, I can't emphasize enough, just don't do that. Do this accidentally. The thumb is that it should either come or this, right? Part of the function, rather than if anything could access this and change it. Or this is gonna, maybe we're doing return x not knowing, then it's gonna have an undesirable effect on any invocations of this. Create some state inside your function. If your function relies on some piece of data, it should either come in through the front door, is when you're writing a function, you want to make sure everything inside the function is everything being used inside the function is in the function, right? Like it's either a parameter or it's a variable being. Y is a global variable here, right? But it's fine to pass y as an argument. If y changes, we can call our function with the variable y, but that changes the output of the function, whereas function calls, which would be weird. It's hard to manage that. The other takeaway is a variable that is created does not live outside this function. So if I try to print x, let's see where x is. X is defined on line 611 inside. If I try to print x at some point, so we're going to get in. So those are the big two takeaways. You can use global variables inside your function, but you shouldn't. You can't use local variables outside of their scope. You just can't, right? So you can see we get name error, x is not defined, 614, print x, that's right there. Okay. Now, let's move forward. Okay, cool. So the integer type. So we're going to go over the scalar types. I know I've mentioned these. We've talked about these. We've brought these up before. We'll go in a little more depth. So integers. What are integers? Well, they're what you think they are. They are positive whole numbers, right? So if a number has a fractional value, it can't be, or what you might call a decimal, that would be considered a floating point number, which we'll get to in a second. So let's look at what an integer is. So -1 is an integer, negative 0.0 value, but they don't have the what integers are. The number. Well, let's see. A good way to think about int type is that it can represent a value that is countable. An int can only be positive or negative whole number. There are many instances in programming where it is necessary to count values or define a position. At such times, discrete values are necessary. See this REPL. Run the experiment for code, manila folders in a box. So for example, what if you count manila folder, we can say num folders plus equals 1, blah, blah, blah. So we can increment the value of this variable with other integers. Convert input into an integer. I'm never really a big fan of doing things this way. Alright, so y and my var. I'm overthinking this at this point. That's what's happening. Let me not do that. Let me underthink this, which is a much better level of thinking. Alright. Cool. Let's just run this. So we're going to get some input into the variable x. Eventually this will run. Input a variable or a value for x. So input prompts the user for input, and the prompt string is provided here in input, so it says input a value for x. So input always going to return a string. So if I put in the number 37, that is, what I mean is the number 37, but the integer 37, but it's going to see this as a string of 37, right? So if we run that, integer, right? So it's going to print that out. So let's see. Oh yeah, so this prints out the type. This is of type x. And then we're going to convert it to an integer by saying x equals int of x, right? And then and it says 37 times 4 is 148. Cool. So you can see we can convert a string into an integer in this way. And let's actually explore that a little more. There's times when you want to do this very thing, so it's kind of worth a string of like 5, and I want to add 5 to the string 10. What's that gonna give me? Right? Is it gonna give me 15? B equals 10, and then math equals a plus b. Type of math, we'll see math as a string. and the value of that string is 510. But it's the little character is 510. Right, so we can actually convert this. If we wanted to get 15 out of this, we could say math equals int and we'll convert each of these strings into an integer, which we can do because they are, ooh, and someday we'll see it run. So this says class int and 15, so that's fixed. What if we did want it to be 510 though, but we still wanted math to be an integer? We could say math equals math, and so this will give us the integer 510. Right, so that gives us some flexibility. We get the so it's specifically with ints in this case. Let's look at something that you can't convert. So we'll say C. So that says high and 510, right? Now I could, because C is a string and A and B are integers. So we can actually cast it back to a string, str. And then that'll C, which is the string high, can we cast that to an int? And hopefully you're with me on this one. That's a big no. If you have an intuitive and obvious way, like single way in which the world, I think it's safe to say that however you might cast a string, any arbitrary string to an integer, there isn't an obvious way to do that. Like maybe do you get the decimal converted ASCII binary code associated binary obvious way to convert. Oh, rounding floats. So a floating point number, it's a number that has a decimal in it. The reason we don't call it a decimal though is because in programming you use a lot of other bases. It's not common, or it's not uncommon to see base 16, which is really just a wrapper for binary. It's a way of sort of condensing binary information. So base 16 is usually known as hexadecimal, and there are different ways of expressing it and denoting that you are expressing a base 16 number. Usually you use 3, 4, 5, 6. A, B, oops. A, autocomplete. C, D, E, F. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's your base 16 number set usually. It doesn't come up often, and we're not going to get into like doing anything with hexadecimal, but it's obviously safe to assume that numbers are going to be expressed usually in base 10 because that's how we're used to expressing them, and it'd be silly to like default to another base, obviously. But as such, we don't call these decimal point numbers because decimal means a part of 10, essentially. That's what it means. So we think about the point as being able to float. So let's just have a big long number here. So the way that it's stored in memory is you have this long number of this long string of numerical characters, and then you can kind of choose which set of characters the point should fall between, right? You can only have one. So this point can float left or right. Oops, that's a comma. Right? So that's why we call it a floating point number. And I'm not going to get into exactly how floating point numbers are handled, in your CPU. Although this is a hardware level sort of thing, the way these data types are structured. Pretty interesting, but also out of the scope of this conversation. So that's a floating point number. A floating point number can express a fractional value between any two integers, right? So between any two consecutive integers, I guess you could say. So here we have 33.51, etc. We have 0.3. We can have negative floats. That's just fine. Negative 40, 400,031. I don't know. Something. .4, right? We 4.0. Let's say that that have the equivalent value to an integer. So we can say 4.0 equals 4. And Python there are other languages where this won't be true, but Python will regard this as true. It regards the value of 4.0, the float value 4.0, to be equal to the integer value 4. And 33.47, the types of those would be equal, because this second line is we're at okay. Right, and that's why I started talking about this, rounding floats. So at some point you're going to want to you're going to have a float value 42.3, and you don't really care that you have the 0.3 or whatever. You don't care about the decimal. You just want to truncate it and convert it to an int and go about your merry way, print. And this is always just going to round down everything after the decimal point. So there isn't any other magic going on there. So this could be 42.999999, and Python will convert it to a floating point. Actually, I wonder if there is a point. Ah, yeah, okay. So it actually does round that one up. I think I did one too many. So I think it's 15 digits of precision. There we go. So I put 15 nines in there, and I guess after 15 decimal places, it starts to wonder. It starts to calculate that as actually just 43. It can't 1, 2, 3, 4, 5, 6. It's a precision that my CPU is literally capable of handling. So now that'll actually round it down. But it's not common to like get into a situation where you can just think about an integer as just chopping off everything after the decimal place in a float value. Okay. Yes. No, right, because integers don't hold decimal places. That's what floats do. Okay, in the example function above, get middle letter. Oh, I didn't read that one. Can a non-integer be used to index a string? The answer to this is no, though. We can't use a float as an index. I need to... Give me 1 second. I just have to take a note to a correction that we're using. We're referring to string indexing, but we haven't talked about it yet. Oh my gosh, Slack. Okay. So this is a good point. We need to talk about indexing, which I'll do really briefly. We're going to get more into that probably in this study hall, but if I do, let's say, oops, I have to make it a string, G-O, and let's say I want to access just part of this string, just like a single letter from this. I can ask for a certain specific letter back. I'll put square brackets immediately after the string, and then I'll ask for the number of the letter starting at 0. So H is going to be 0. So if I ask for the 0th element, so 0, 1, 2, 3, so that'll be L, and it'll be the second L, right? So even though there are 5 total characters, it has a length of 5, its top index is 4. So 0, 1, 2, 3, 4. So that'll be the O in there. So when you're indexing, and this, so hello sub 4 gives us that O, and when you're, an integer, because if you think about it, like what would a decimal like even mean in this context? In these two characters, there's assertion that can be made about what's in between those two characters. So that's going to give me an error. And the same, yell at me and we'll see. Okay, so this actually ran. So it says string indices must be integers, not floats. 3.0, that'll give me an error. So write a function, divide by 7. Okay. So def divide by 7 as an argument or parameter. We could use the word parameter in this case. I usually do call it an argument at this point, even though that is technically incorrect, but everybody does it. So the function will divide the number, our input in, by 7 and return the result of that operation. So 7, shorten this by just saying return in over 7. Let's run that test. Meh. Result should have been 14. Oh, okay. Result. Oh, I can just cast the result as an integer. I read that and then promptly didn't do it. Here we go. So if you have an operation that's going to result in a float and you want it to result in an integer, just wrap the operation in parentheses and throw int in front of it, and that will pass the float that in over 7 returns or evaluates to into the int function, and it'll cast it as an int. Get an int returned. Okay. Floating point numbers. Kind of talked about this already. So simply put, floats are decimal numbers. These can be thought of as measurements or the results of division or calculations involving other floats. As such, floats can be thought of as continuous. You can express a number very high precision, right? So you as I showed above, actually, it'll be accurate out to 15 decimal places. We want to represent the probability of pulling a red ball out of a bag that has 30 red balls and 60 green balls. So we can say red ball, well, let's just do a new one. Cool. Third, right? So, and that's what we expect. So if we have 30 balls and 60 balls, so there's 90 red, 30. So it makes sense that we get 3.333 repeating. And actually, I think if we count these, if we count them, so 1, 2, 3, 12, 13, 14, or digits, excuse me, not bits. Cool. So the above example shows what I would just say a use of the float data type. A single slash always renders a float. You might imagine that any value is converting it to a float instead of an integer. And that conversion happens in the same way. Number equals into a float like this, because a float, so we started with 10, what are we going to get out? You have plenty of time to think about it while my extremely weirdly slow interpreter thinks about it itself. Okay, so we're going to get 10. It'll show us that it's a float. It's simple to say that 3 and 3 are equal to each other. However, numbers of the float data type have decimal points. So it is important to decide what the threshold of equality should 3.0 might be close enough for some calculation, and thus should thus be thought of as equal. So for this reason, explore this example of equal enough function. Interesting way of doing it. Okay. Do that. Let me just clean this up a little bit. Blah, blah, blah. Let's see what it does. So we're going to take in float 1 and float 2, and then we'll return true. We'll say true that it's equal enough, close enough. Maybe we should call this close enough. Good. Yeah, and let's actually see. I'm just curious. I'm not exactly sure at what point this will happen, but let's say 3.01 equals 3.0, and let's just keep adding zeros to that first one and just see how deep this rabbit hole goes. Real quick, let me just get a few more of these. Actually, let's see. Let me do all these at once so I don't have to wait for the code to run every single time, because that's kind of a pain. Okay. But let's just see. These are the kind of experiments that you can do, you know, obviously you can do these yourself. Cool, look at that. So we got to the point, these last, you know, these two, it's so precise that Python itself, well, it's actually not really a limitation of Python, it's more compensated for in other ways, but it's sort of a just accepted ceiling of accuracy with those super precise floats like that. Just take a note of this. And this one is also true. True. Okay. So underflow. As a side note, you should familiarize yourself with attempting to calculate a number smaller than what can be stored in memory. As alluded to before, integers are stored differently than floats. So that is true. The way you're very different under the hood, even though to us they seem similar. To the computer, they're very different data types. An integer is more or less a direct representation of its binary form. 0, 0, 0, 0 is 0, 0, 0, 0, 1, etc. So for example, here are the binary representations for integers from 0 to 15. If you can't read the binary, don't worry about it. It's not important. This is just sort of if assuming only positive numbers greater than or equal to 0. Structure of a float is convert from a float representation to decimal. So for now, the key takeaway is that you can just quote unquote count binary for a float. And well, I was hoping to get it because the computer can't represent. I can put zeros in my text editor to express this value, but point it has to just assume that this is just equal to 3. And that phenomena is called challenges. Data type with extremely small numbers. Extremely precise floating point numbers, you may need to work around this phenomenon. And there are ways of circumventing this kind of underflow and getting more precision out of a limited precision, or out of a limitation. So which of the following statements is not true? A float can only number of bits it has been allotted in the memory. When comparing floats against each other, Python will automatically check if they are quote unquote close enough to being equal. I think that's not true. When comparing floats against each other, yeah, no, that's not true. An integer can be converted to a float by the use of the float function. That is true. A float can be assigned to type differences between int and float when making calculations. Yes. So there is interoperability between. You can do something like going to result in 8.9. It's going to result in a float because the resulting sum can't be expressed as an integer. So it has by 3. What is wrong with me? Spelling 3 with 2 I's. That's like the new cool. You probably haven't heard of this spelling before. Sorry, I'll stop that. which it then multiplies by 3n times 3. Probably going to want to capture that or return it or do something. And then returns the result of the I can't do that shortcut in this environment. So used to it. Return float n times 3. Boom. Hooray! The Boolean type. So by the end of this lesson, you'll be able to comprehensively describe the Boolean data type. So values, obviously, integers can express like underflow, but obviously you can express a whole lot of numbers. And in a more abstract sense, integers represent the infinity of integers, infinities of numbers, but can also represent the infinity of precisions between the indicative integers, right? So suffice it to say, there's a lot of floats in it. Booleans, there's only 2: true, false, which is pretty nice. And it might seem like, well, that's a cute little set of values for a data type, and you maybe won't use it a lot, but you do end up using Booleans a lot. Understanding Booleans isn't a matter of understanding like what they are. You now know what they are. It's a data type that can have one of these two states, one and only one of these two states. Understanding Booleans is understanding like where they crop up, what they're used for, because they are very useful, and what kind of expressions express a Boolean or evaluate to a Boolean. Okay, so you've seen the 4 equals 5. We know 4 is not equal to 5. This double equal is a Boolean type operator, because, or you can also call it a comparison operator. And what it does is it compares the thing on the left with the thing on the right. Probably pretty intuitive what this does. States that an expression like this could conclude with, right? Like, is 47 or an integer or a float, or is a string a reasonable outcome? No, right? There's no easy or obvious way to think about this as like evaluating to anything other than this expression is either true or it's false. So the expression 4 is equal to 5, the statement 4 is equal to 5 expresses the value false. I'm using that word expression because it expresses it, it gives it back. So 4 equals to 5 expresses the value false. And let's just put our eyes on that. And obviously, 5 equals 5 is going to be true. But there are other comparison operators, and let's look at a few. We can say 4 is greater than 5. That's going to be false. And we can also do less than or equal, or greater than or equal. And we can also do not equal, which is exclamation point equal. So let's just see what we get here. Um, 4 is less than 5 is true. 4 is greater than 5 is false. 5 is less than or equal to 4 is false. 5 is greater than or equal to 4 is true. Cool. So these are the sort of operations, or Boolean operators, because they make a of these equal to and not equal to. I think it's safe to say are the most used. I'll comment these out. So and, or, and not. So and is going to take two. It's like a Boolean operator that whose left hand and right hand arguments are other Boolean expressions, right? It's false, right? And we can just imagine these as any arbitrary expression that evaluates to true or false, whatever. And then I'll print A and B, and actually, oops. Oh, my editor is freezing. That's lovely. Okay, sorry about that. Hopefully this is gonna work now. Wonder what that is about. Okay. Oh boy, that's taking a long time to run. False, false. Just an example of some and is going to return are true, right? So if A is true and B is false, and is going to return false. If either one is false or both are false, A is true, then OR will return true. If B is true, then OR will return true. If they're both true, then OR will return true. Take whatever in was false here, right of it, and it's just going to inverse a Boolean. Cool. Another common style of but and 8 in this list, 7 in 5, 3, and 8, and that's going to be false. That this statement is false. Something where you can say cells are kind of similar, where you end up doing that a lot, or you can. I find this very useful. So these are your sort of, so you can see Booleans themselves are pretty simple, right? There's not really a whole lot going on there that result in Boolean. You have these sort of comparison operators. I'm using integers in this case with these top two, equal to and not equal to. These can be applied to between any greater than or equal to these and false. And then we have ways of combining Boolean expressions, right? And just to be clear about this, I could say print like 4 less than 5. And I'm going to put parentheses around this just to kind of control my order of operations. 4 less than 5 and 5 equal to, or like, let's say 5 not equal to 7. So we want this whole expression to be true. Let me just get some extra space in here so we can read this a little better. So we want this whole expression to be true, this outer expression, if the left hand operand and the right hand operand are both true, right? So 4 is less than 5, that's true, and 5 is not equal to 7, that's also true. So we should expect 4 less than 5 and 5 not equal to 7 to be a true statement. Just a pile of truthiness, and many other languages have this. There's this idea of truthiness and falsiness. So before I've done things where I've said, like, is there any obvious way to convert this string to an integer, right? So, and you know, some string of arbitrary characters, or of an arbitrary character, unless it's a single, or unless it's the string of like number characters, there isn't an obvious way to convert that string into an integer, if they're not digits. So the funny thing about Booleans, and this might be a little counterintuitive, but every other type can be cast as a Boolean and can be associated with being truthy or falsy, right? So a string that's empty, and what I mean by that is literally empty, not a string. This is not an empty string, right? This is a string with a space in it. You could have a string with a bunch of spaces and a new line character, for example, right? This is a string with invisible characters in it, right? So when I say an empty string, I mean empty. String is false. False. In the string, a single space, multiple spaces, a word, a sentence, something, whatever, a grammatically incorrect sentence, an empty string is falsy. Okay, so that's to a bool. -8, 0.0, or 0.001, or negative zeros, etc. Yeah, that's good. So let's see what we get for this. And this might not behave quite like you expect, right? So notice the first two are true, 3 and -83 are true, 0 and 0.0 are false, and then the last two are true. 0.01, even though it's close to 0, it's still not 0, so that's true. And then -1.8, that's true. So if a number is negative, it's truthy. Whether or not it's, this is going to apply to integers as well as floats. If it's negative or positive, it's truthy. If it's 0, it's falsy. And by 0, I mean literally 0, not close to 0, but 0, right? And obviously we can cause an underflow if we just go way out and just add a bubble. We'll just leave it like that. So that's still going to be truthy. Cool. All right. So that's true for none as well, right? So none is going to be falsy. I suppose that's worth just showing explicitly. Bool, none. So none is a value that's, that's unary. It has only one state, whereas Boolean has two possible states. None has only one state. And it's the value, you might be able to infer this, but it's the value you give something that has no other value. So none is going to be falsy. Truthy and falsy. So these qualities of a bool data type. What if what if 0 should be a true value? Right. So what if there's a scenario where you want to do something, you want to do something, you want to regard 0 as truthy. You don't have to change anything like fundamental about Python to do that. You can just say not bool 0, right? So bool 0 is false, not false. Falsity is not truth. Comparison operators, greater than, less than, cool. Challenges. So the bool type is only directly applicable to the exact true. Let's just say true. I don't know. I don't really. I want to go rewrite this question. I'm not sure about what that's asking there. Directly applicable. Yeah, I mean, I guess false is the right answer there, but that's an oddly expressed problem statement. First values can be considered to be false. Okay, we're just going to skip that. Yay, function. So write a function. Is difference truthy? Is difference truthy? Oh. As arguments. It will subtract the two arguments and then return the result of the Boolean. Well, so I'm presuming it subtracts them in order, so n minus m. So if we do subtracts them and returns the result cast to a Boolean. Good. Always. Return bool of n minus m. Invalid syntax? No. Oh, I probably just spelled the thing diff with difference with 3 f's. That's this cool new way to spell difference that I invented all by myself just now. Okay. Write a function called is greater than. We'll take 2 parameters. Num2 is greater than or equal to num1, return true. Or equal to num1. So I'm going to do this with a condition here. We'll return true, else return false. So this will work. This will work. And also this will work. That. Greater than or equal to num1. Since this literally results in a Boolean value, I can just return it, since it's going to return true when I want it to return true. So describe the string type, cast values to a string. So strings are really a really useful data type. If something can't be cast to anything else, generally it can be cast to a string. Rules about how they can be cast to other types, but a lot of times I kind of think of them as sort of a universal, basis. If you like, you can always deal with the textual representation of something and get a lot of mileage out of that. Oops. I guess what I'm trying to say is you do it a lot. You end up very light introduction. This lesson is a very light introduction to strings, to the string data type in Python. There will be several additional units covering this data type in greater depth later on in the course. A string is a collection of characters. In simple terms, words, sentences, and paragraphs would all be represented in Python by the string data type. However, numbers can also be represented in strings such as, in quotes, the string 1, 2, and 3. Such a string cannot be manipulated mathematically without converting it to an int or a float first. So, all right, declaring a string. So we can use single quotes, and that's single quotes, single tick quotes, or double tick quotes, and they function exactly the same. Little side note here, PEP8 specifies that string. The single tick though is it's because there's something, right? Because Python can't. Why I like to use double tick quotes. Now you can choose to do what I do, or you can follow PEP8 convention. To break PEP8 convention, then you have to adhere to that style guide. It's okay to break convention, just have a reason for it and do it consistently. So I don't use single tick quotes to declare strings unless there's a reason for it, and it's the exception for my code, not the rule. You can do whatever suits you. So to declare a string, my string equals a string. Hey there. Oh, hold on. I think somebody's just knocking on my door. Only 1 second. Sorry about that. Somebody just came in to chat with me for a second. Okay. So string concatenation. So concatenating. This is a good one. So you can add two strings together to make one string. So I say, hey, I'll put a space there, plus, so another variable name, and name will be my name. Hey, and then the variable called name, which is my name, and we'll say print my string, and that will print hey Clark. String literals. So this could also just literally be name or something like that, and that would work as well. And that's what's being shown here, like hello and you. Full string is string 1 plus string 2, and that'll say hello you. String assigned to it. So we can concatenate the 3 strings in order to assign them to a new variable final string. So let's concatenate them. So presumably first plus second plus third. So, and I think in an example like this, oops, I don't need to actually save it. It's just such a habit. Examples like this, go ahead and pop them in your environment and go ahead and run them. That didn't even run. Oh, I'm being silly. I didn't ask it to print it off. So this is the first part of my sentence. There we go. There you go. So when we're adding, oops, oh, I canceled the tests? Okay, that's what happened. So when we're adding strings, we refer to this as concatenation. When you're adding any collection that can be concatenated, we refer to that as collection or concatenation instead of adding. Sometimes we'll say adding because obviously it's very much like adding, but the technical term is concatenation. Okay, so in the following challenge there are 3 variables, first, second, third num. Each of these variables has an integer assigned to them. The point of this exercise is to concatenate the numbers and turn the result back into an integer for the final assignment to the variable final num. See below for examples. Okay, so given these numbers, print final num. Okay, so this is what I always look for, is like an example containing the output, right? So the intended output is 156975. So that'll be 15 plus this plus 975. Good. That should be easy. So if I return, or I'm thinking about it as a function, we'll say int of stir first num plus stir second num plus stir third num. There we go. Cool. Create 3-digit num. The function will take in the function will take for the parameters in m p and combine them into a single 3-digit integer. So that'll be int stir n plus stir m plus stir p. Your function should make p the first place, m the second place, and then n in the third place. Okay, there we go. So 298 should, oops, I keep hitting. Cool. Okay, so you can see what I did here. So take note of the order that I do this in, right? Because I look here and I see this function will take in 3 arguments, combine them into a single 3-digit int p the first place, so stir p plus stir. I mean, from here it's just whatever order they go in, right? So that's something to do. I'm a big fan of this, like, do the thing that you know you need to do as soon as you know you need to do it. So I know I need to return an int, so I just write that int right out of the gate. And then I know I'm going to order these in some way, and so I just put them down there, and then I read the rest of the problem statement and said, oh, okay, these need to come in a different order. So I just changed that order. So Yeah, it's a good workflow habit. All right, cool. So it's a few minutes after the hour. I think this is a good place to wrap up. Next time we'll start in on the none